Good evening, my dear students, and welcome to this session. My name is Anoop Vashishtha and you are on Unacademy NEET Elixir channel, where we are finishing off the chapter called The General Principles and Processes of Isolation of Elements, which is better known as metallurgy. Today we are going to talk about some extraction of some specific metals like iron, copper, zinc, aluminium, and then we are going to talk about the methods of refining of these metals. Now this topic is not that long topic, nor it is a difficult topic. It's quite an easy topic. So here we are going to do it nicely, easily and thoroughly. Yesterday in the class we had a long class of 2 hours in which we have done most of the topics here. Now we are going to finish off with this chapter. This chapter is to be done once. That would be enough for this particular chapter. If you do it once, that would be very much enough. And let's begin over with it. Jeete beta Akshay, Priyanshu Ghosh, Jeete beta Radhika Mittal, Tirthraj Mukherjee. Very, very welcome to this particular session. We have 10 students watching in this class. And so, let's begin with the chapter. So, Elixir dropper batch is bound to start from 16th of August. We are having the Elixir dropper batch for NEET UG 2024. Clear? The timings are set: Botany 6:30 to 7:30 p.m., 7:30 to 9 p.m., 9 to 10 p.m. And please remember, we are very soon coming with the individual batches. That is, you are going to get the selection of the batch. Like you can select for chemistry, you can select for botany, you can select for zoology, you can select for physics. Yes, physics also is going to be started very, very soon. You are going to talk about the different batches separately as well. So apply the code WS Live, or the better code would be you apply the code AVLIVE. One of the students have already applied this batch and they have selected for the batch Elixir dropper batch. You also can join with us. Hello beta Faiza Khatun, how are you? Arman Ali. Arman Ali, this batch is so much Hindi that you may ask me what exactly is to be asked and I'll explain it. But majority of the times we are going to stick to English. Okay, Arman Ali, use Hindi. Yes, I'll be using Hindi as per the requirement. So that's me. And now I begin over with the chapter called metallurgy. Now let's talk about a process which we call as a thermite process. We are talking about the extraction of iron from its oxides using the thermite process. What exactly is the thermite process? It's a very, very important process. Now when we talk about the thermite process, it is a specific reaction. This is the container that we have. Now thermite process can be done. Maybe some people would have seen that particular serial, the series, heard of something called, very famous series called Breaking Bad. Now that Breaking Bad also has a mention of this particular process where they break a lock using this particular process. Now this process is highly exothermic reaction. The reaction is simple one. We have Fe2O3, that is ferric oxide, and it is reacted with aluminium. Aluminium is a highly electropositive element, it's a highly reactive element, and while Fe2O3, iron, is less reactive as compared to aluminium. Aluminium has a very high affinity towards oxygen and it can extract oxygen from iron. This thermite process can be initiated by a little bit of heat to be supplied here. KMnO4, barium oxide here, this is applied, it is magnesium ribbon which is used, and it converts to iron and Al2O3. The important thing about the thermite process is that this iron which is obtained is molten iron. Thermite process is not used to produce iron, it is used to produce molten iron locally. Now this thermite process is used wherever we have to require molten iron to fill the gaps in iron, that is the joining of the railroads, maybe in the bridges. There the thermite process where it is used as thermite welding is used. नहीं बेटा आज स्पेशल क्लास नहीं है राधिका. ओके, अक्षय कुमार सेज मैंने ये प्रोसेस लाइव देखा है होते हुए. ग्रेट. तीर्थराज मुखर्जी कह रहा है इज दिस फिजिक्स? नो, इट इज नॉट फिजिक्स, इट इज केमिस्ट्री. You're asking me, Tirthraj? Okay, so that's what we have as thermite process. As you can very well see, this is such a strong process, such a high energy process. Okay, now that was the thermite process, and now we have another process which we call as the extraction of iron from oxide, the blast furnace. Why this furnace is called the blast furnace? This is called a blast furnace because here the furnace is heated by a hot blast of air. Here we give the hot blast of air which is moving in, this hot blast of air. That is why it is called the blast furnace. This blast furnace has various zones. There are various zones in this blast furnace. From here, we get the blast of the air. This is the blast of the air. Now, when we talk about the blast of the air, this becomes the first zone, which is called the combustion zone. The combustion zone is there where we have the combustion of carbon taking place. Carbon gets converted into carbon dioxide. It's an exothermic reaction. The temperature rises to a very high temperature. This coal, in fact, which is used, it is anthracite coal and it is heated further. So it is coke. It is pure carbon which is heated here. So this pure carbon which is heated here, it is able to get the temperature to something like 2000 degrees Celsius. In fact, 1900 Kelvin. नहीं बेटा ऐसा सरप्राइज नहीं है अभी, ठीक है. You are going to have the special class tomorrow. Tomorrow evening you are going to have the special class, and tomorrow, remember one thing very important, tomorrow we are going to start in the morning at 10 o'clock with equilibrium chapter. So tomorrow we are starting with the chapter called chemical equilibrium. This is a very, very important chapter. This is the most difficult chapter that the student consider. We are going to talk about the chemical equilibrium. We are going to talk about chemical equilibrium in two classes. In the morning, 10 o'clock, we have the chemical equilibrium class, and in the evening, 4 o'clock also, we have the chemical equilibrium class. Okay, so be prepared. Till that time, you are not having the other classes. The chemistry classes are taking the maximum time. So be very clear with it. Okay. So this is what we have as the combustion zone where the ignition takes place. Now, when the gases rise up, at that time the gases become a little colder as they rise up, because here all the reactions that are taking place are endothermic reaction. Then comes the fusion zone. When we talk about the fusion zone, the iron which is falling from above, this iron, which we term as the spongy iron, this is solid. So it gets the heat and it becomes Fe liquid. Now this happens in the fusion zone. Okay. Above that, at this point, 1273 Kelvin, that is what we have as the slag formation zone. Slag formation zone has many reactions taking place. CaCO3. First of all, it gets heated up to form CaO plus CO2. This CaO reacts with the silica present in the ore as impurity to form CaSiO3. Now, this is what we have as the slag. In addition to that, one more reaction takes place. This carbon dioxide which is being formed, it reacts further with carbon to form carbon monoxide. That is what we have as the slag formation zone. All these reactions are endothermic reactions, so the temperature is decreased. These reactions consume the energy from the hot blast of air. So the temperature decreases. And there comes the reduction zone. Please remember, when we talk about the blast furnace, the reducing agent is not carbon, but carbon monoxide. Here, Fe2O3 would react with thrice of carbon monoxide to give 2Fe plus 3CO. Fe2O3 plus 3CO gives us 2Fe plus 3CO2. This is what we call as a spongy iron. The spongy iron, because here carbon monoxide removes all the oxygen from the lattice of iron oxide, and what is remaining is the structure of iron. So this becomes quite porous iron, and that is why it is called the spongy iron. So that spongy iron is formed in the reduction zone. Beyond that, the temperature further decreases to 473 Kelvin. 473 Kelvin temperature, this is the temperature which is enough to remove the moisture from the ore, but it is not there to do any other changes. And then these hot gases, they move out. This is a cup and the cone arrangement which consists of the charge. The charge consists of the ore, it consists of the flux, and it consists of the reducing agent. The ore is Fe2O3, flux is calcium carbonate, and reducer is coke. So that is the mixture which creates the charge. Now here the slag is formed, the molten iron is formed. The molten iron is placed in huge molds made up of clay, made up of sand, and that huge molds, they create what we know as the pig iron. Now pig iron has near about 4% of carbon present in it. The carbon which we have added is more than the carbon which is required for the entire reaction taking place. So we have a bit extra of carbon. So this pig iron contains more of carbon. So here we have got the slag. Slag is the molten material floating over the surface of the molten metal. It prevents the reoxidation of the metal. See, here we have the hot blast of air. If the metal is exposed to this hot blast of air, the metal is going to get reoxidized. Is it clear? Okay. Those who have not liked the session, go ahead and quickly like the session. So that is going to be the blast furnace. So here we have the old blast, how we used to get the blast furnace. Okay. So these are the reactions taking place in the blast furnace at 500 to 800 Kelvin, that is lower temperature range in the blast furnace. Fe2O3 is first reduced to Fe3O4 and then to FeO using carbon monoxide. Okay. Then this FeO gets converted into Fe2, 2Fe plus O2, carbon gets converted into carbon monoxide and carbon dioxide. So that is what we have as the extraction of iron, and this is what we have as a Lingam diagram. Now, the iron obtained from the blast furnace contains about 4% of the carbon and many impurities in smaller amount like sulfur, phosphorus, silicon, manganese. This is known as the pig iron. Now, it can be molded into variety of the shape, but when it is molded into variety of shapes, this is called the cast iron. Cast iron is different from pig iron and is made by melting pig iron with scrap iron and coke using hot air blast. It has slightly lower carbon content, around 3%. So that is what we have as the cast iron, and is extremely hard and brittle. The most of the objects which we get where we require the strength, we require only the hardness, it is made up of cast iron. Pig iron is not used to make anything. Pig iron, when it is again molten, it converts to cast iron. Fine. Now when we have wrought iron is the purest form of commercial iron that we can get. So this is what we have as a purest form. Here entire coke is completely burnt by heating it with ferric oxide. So it is prepared from cast iron by oxidizing impurities in a reverberatory furnace lined with hematite. Hematite is Fe2O3. Now Fe2O3 becomes the oxidizing agent, carbon becomes the reducing agent, they react with each other, leaving behind pure iron, and carbon dioxide is released out. So the hematite oxidizes carbon to carbon monoxide and we end up with pure iron. Copper, now this is what we have as Bessemer's converter. This is what we call as Bessemerization. I told you this is auto reduction process. Yesterday only we talked about what is Bessemerization. So this process is what we call as auto-reduction. This is process what we call as Bessemerization. Those who have not liked the session, go ahead and like it. These are the reaction. Here copper sulfide, the oxidation is taking place. This is what we have as roasting. The first part is roasting. Second part here, this part is what we have as calcination. This part is the slag formation. Is it clear? Fine. Then we can have extraction of zinc from zinc oxide. Remember, zinc is more reactive as compared to iron. So zinc is not easily reduced by using carbon monoxide. Zinc is reduced by using carbon. Further, zinc is what we know as a volatile metal. Zinc is the volatile metal. So when zinc oxide is heated with carbon at a high temperature, zinc is obtained in the vapor form. In fact, you need to understand that zinc, cadmium and mercury, they are purified using distillation. We are going to do this a little later. So these are purified using distillation. Now, there is one simple question. Cr2O3 plus 2Al giving you Al2O3 plus Cr. This again is a thermite process. The reaction is quite favorable. The delta G is highly negative. Why does this reaction does not take place at room temperature? The answer is again very simple. Why does the reaction does not take place at room temperature? Because this reaction requires very high activation energy. This reaction requires a very high activation energy. Is this clear? Now let's talk about the extraction of aluminium. The extraction of metal by electrolysis. Okay. When you talk about this particular reaction of metal electrolysis, then in that case here we have certain things. Al2O3 has a very high melting point. Now Al2O3 is practically dissolved in cryolite, and cryolite is the flux which has been added to this particular reaction. Now this particular thing is, why am I saying that Al2O3 is practically dissolved in cryolite, is that here we have 95% of the cryolite and only 5% of alumina. So it is only 5% Al2O3 mixed with 95% of cryolite. And cryolite क्या है? Na3AlF6, and this also contains CaF2 and certain other things also are there. CaF2 होता है, Na3AlF6 होता है, and then we could have some amount of lithium carbonate also. So many other things. Now these impurities, what they do? What is the function of the cryolite? The function of the cryolite is to reduce the melting point of ore. It is to reduce the melting point of ore, and in addition to that, it increases the electrical conductance. It increases the electrical conductance. So it reduces the melting point of the ore and it increases the electrical conductance. These are the two functions that the cryolite does in extraction of aluminium. Here we have the entire container. This is the steel container. The negative is the carbon cathode and the positive is the carbon anode. In this particular reaction, the anode is actually consumed. It is being consumed in this particular reaction. How this reaction is consumed? the Hall-Heroult process. At the cathode, aluminium absorbs 3 electrons from the negative terminal to form aluminium. Fine. And at the anode, the carbon reacts with oxide to form carbon monoxide and carbon dioxide. Now, some amount of carbon monoxide is formed, some amount of carbon dioxide is formed, both the reactions are taking place. Clear? Now, when we talk about both the reaction taking place, for each kilogram of aluminium which has been formed, around half kilogram of carbon is consumed. So, this graphite electrodes which are present here, these graphite electrodes are slowly consumed and they need to be replaced periodically. So, that is what we have here. So, this is what we have as the extraction of aluminium. Okay, aluminium has a higher density as compared to the molten aluminium oxide and Na3AlF6 mixture. So, aluminium is tapped out from below. Okay, this is what we have as Hall-Heroult process. Now, this is the question from NCERT. At a site, low-grade copper ores are available and zinc and iron scraps are also available. Which of the two scraps would be more suitable for reducing the least copper ore and why? Zinc is more reactive as compared to iron. So, preferable would be zinc because it is going to react much faster. But actually, it is iron which is used because zinc is much costlier as compared to iron. As far as metallurgy is concerned, cost becomes an extremely important factor because it is an industrial process. So, it is the iron would be used. Where is iron? Iron. This is preferred. Why is it preferred? Because it's cheaper. Is this clear? All the people in this session, I believe you have already liked the session. Any confusions? Anything you want to ask? Okay. Now we get along with the refining of the metals. Now, these free metals which are obtained in these processes, they they always contain some impurities. Now, these impurities, they give some positive and some negative properties to the metal. Most often they make the metal brittle. Metals are mainly used for the structural purposes, and these making the metal brittle is going to be an extreme large flaw in the structure of the metal, because these metals, when they are used as structural material, being brittle would mean that whenever it's going to be struck, it is going to just shatter, and we don't want that. These impurities were the reason that Titanic sank. The steel used in Titanic had a triple more amount of sulfur, and because of that triple more amount of sulfur, the Titanic steel became brittle at the temperature at which the Titanic was sailing. So, when that iceberg struck Titanic, the steel which was used to create Titanic actually shattered. Had it been having a little less amount of sulfur, then in that case this steel would not have shattered, rather it would have bent, dent पड़ जाता, वो टूटता नहीं. The slight small amount of impurity of sulfur was enough to sink the unsinkable ship known as Titanic. Is that clear? So, they have several impurities which may be other metals, which they may be non-metals. Like if we obtain sodium, potassium becomes the common metal that is separated along with sodium, and potassium becomes the impurity here. In any case, most of the time the removal of the impurities is necessary. Sometimes it is for just greed, like in copper refining. The copper refining leads to the formation of gold, silver, platinum as impurities. So, the copper refining is dual purpose. One, it gives pure copper, and second, it gives the entire cost of refining in the terms of precious metals. So, that is what we have impurities. Now, let's say we talk about the purification of the metals. The various processes which have been mentioned in the NCERT for purification is distillation, liquation, electrolytic refining, zone refining, vapor phase refining, and chromatographic methods. Now let's get along with these processes one by one. Anybody has to ask anything here? Any questions, anybody? I don't think so. And I believe I have already shared with you the metallurgy chapter on the Telegram link as well as on the WhatsApp link. So you would have your NCERT books open in front of you. So let's talk about the processes: distillation, liquation, electrolytic refining, zone refining, vapor phase refining, and chromatography. And we are going to talk about the basis of each and every process. What are the bases of each process that we have? Fine. So let's get along with the first process, and that's called distillation. Let's talk about distillation. Okay. Distillation, quite obviously, is for the volatile metals. Distillation is for the volatile metals. Volatile metals means they are easily evaporatable. Like out of zinc, cadmium, mercury, zinc has the highest melting point, and that melting point is only 420 degrees Celsius. 420 hai ye. These metals can easily be heated and distilled out from their impurities, and their impurities have much higher melting point. Like zinc oxide has a higher melting and boiling point as compared to zinc itself. So these metals can easily be separated from their impurities by distillation. Here this is an iron retort which is being heated. Zinc goes into the vapor and it's cooled in the container under water. So that is how zinc can easily be extracted, easily be refined. Okay. So that is distillation. They may ask you the question, which of the metals are purified by distillation? If you haven't read NCERT and if you haven't attended the lecture, then in that case you would say, oh, metal distillation. No, but these metals are purified by distillation. Good evening, beta Durga Prasad. How are you? Why are you late, Durga? Okay. Now we have the process called liquation. Liquation is the process which is used where the metals have a lower melting point as compared to the impurities. Now, liquation is used for the metals which are easily liquefiable like lead and tin. So, liquation method is used for lead and tin. And in the case of liquation, what we have is, we have the sloping hearth, and here we have the metal, the impure metal, the sloping hearth. Now, here we heat it, the metal melts and moves ahead, while the impurities are left behind. The impurities remain behind, molten metal flows down, and that is how we are able to separate the molten metal from the impurities. Is this clear? So here liquation method, lead, tin, bismuth, they have low melting point compared to the impurities in the metal. The block of impure metal is placed on a sloping furnace, which we call as sloping hearth. The temperature of the furnace is maintained a bit above the melting point of the metal. To be refined, the metal melts and flows off the slope, which is then collected and cooled. So this is what we have as the liquation method. Anything else you want to ask? I hope I am able to get the chats. Those who have not liked the session as yet, go ahead and like it. Now we have certain oxidation method. Okay. When you talk about oxidation method, it is a simple method which is mainly used for iron. Here the impurities are more oxidizable, more easily oxidizable as compared to the metal itself. Something like in the case of iron, the carbon which is present as the impurity is itself a strong reducing agent. So that strong reducing agent being carbon is able to get oxidized in preference to iron. So this is an oxidation method. In fact, we are using maybe oxygen is used to create the steel. Oxygen is being used if you, I don't know whether you remember or not, when we talk about the corona time, majority of oxygen was provided by iron and steel industry because they have the plants to create liquid oxygen. So those were able to provide that oxygen. Okay. In case of pig iron, the non-metals are present as impurity. When air is passed over hot molten pig iron, these non-metals get oxidized to carbon dioxide, sulfur dioxide, phosphorus pentoxide and can be removed easily. Clear? So that is how the impurities are removed by oxidation method. Now we have the electrolytic refining. Now electrolytic refining is most often the best example which we use is copper. In fact, electrolytic refining can be used for most of the metals up to zinc, even the gold can be refined by electrolytic refining, silver can be refined by electrolytic refining, and even aluminium can be refined by electrolytic refining, but then in that case it is going to be molten electrolyte as the electrolyte, molten cryolite as the electrolyte rather than water. Fine. But it is zinc, copper, tin, lead, silver, gold, they can be refined. They can be refined by electrolytic method. Here we make the impure metal as the anode, that is the positive terminal. So here it is impure copper anode as the anode, impure copper. And here we have the pure copper, thin strip of pure copper as the cathode. Now here it is going to be a reactive electrode. In the case of electrolysis also we talked about this particular process in which one of the electrode is consumed while other electrode gets thick. When we talk about the anode, the copper ions are going to move towards the solution from the copper anode and they are going to deposit on the copper cathode. Whatever impurities are present in the copper anode, they are going to fall down and are going to be collected under the copper anode. This is what we call as anode mud. Now this anode mud, you might be saying it is mud, but this is quite a precious mud because this contains gold, silver, platinum, these metals as impurities. So this anode mud is further refined and these precious metals are collected from it. Is that clear? So this is what we have as electrolytic refining of copper. Now this question has been asked line by line from NCERT in IIT Advanced. Which of these are true? Which of these statements are true for electrolytic refining of copper? In this case, what happens is anode is consumed, cathode becomes thick, the concentration of electrolyte does not change, the impurities are collected as anode mud. These impurities contain precious metals. So that is what we have as electrolytic refining of copper. Anybody has to ask anything here? Any confusions? Anything you want to ask? Now, the very famous method. This method has been asked I don't know how many times. This method has been asked in the board examination, but now the board examination and as far as CBSE is concerned, this chapter has been deleted. So I don't know. This is the topic called zone refining. Now what is the principle of zone refining? What is the basis of zone refining? The basis of zone refining is that impurities are soluble only in molten metal. Impurities are soluble only in the molten metal, and this can be actually proved at your home. What you do is take water, put some salt in it, shake it well. The salt is going to get dissolved. Now put that water in your freezer, okay, and let it cool down. When it cools down and it freezes, you will find that salt separates out as crystals. Okay, remember Distillation is a method of purification of water. Freezing also is a method of purification of water. The icebergs which are formed by freezing of the sea, they contain pure water, although they are formed from salt water. Is that clear? So that is the principle of zone refining as well. Now, somehow they make this particular diagram. It is very difficult to understand this diagram. Well, I'll make a simple other schematic diagram. Now, this is the rod of the metal. Zone refining can be used for any metal. For that matter, अगर theoretically बात करें तो ये किसी भी metal के लिए use किया जा सकता है. Any metal we can use for zone refining, but it is mainly used for semiconductor material, something like germanium, silicon, boron. These semiconductor material in which we need very pure metal and we cannot use distillation for them, then we use zone refining. Okay. So what happens is, this is what we have as the metal rod. Zone refining is also used for that particular metal in which the metal cost is not much. Like silicon, if we talk about silicon, silicon cost is not too high, it is just obtained from sand. ये बात आपको इस बात से भी clear हो जाती है कि whenever you talk about your old phone, the new phone might be costing maybe ₹1,00,000, but if you want to sell an unusable phone, it is not going to be sold even for ₹50. Although it contains everything that was there in the phone, but the moment it is unusable, it becomes dirt. Okay, maybe that lithium ion battery might be sold for a bit more amount because of recyclization, but otherwise they simply say that you just drop your phone in that collection bin to be recycled. They won't give you a rupee for it. If it's working, that's a different case. If it's not working, the material costs nothing. So here we have the rod, and here we create a circular heater. We have a circular heater. Now what they do is, using this circular heater, it is heated to a temperature slightly above the melting point of the metal, and then this molten zone is moved, it is pushed further. With that, the molten zone, when it shifts, here the metal melts. When the molten zone moves, the metal crystallizes, but the impurities move along with the molten zone. Keep on moving it, reach here, take it out, again comb it, again take it, and in every go, the impurities move along with the molten zone and they collect at the end of this rod. Cut this off, throw out this impurity piece, and this becomes the pure metal. So that is what we are using as zone refining. Am I clear? The principle of zone refining, is it absolutely clear? Okay, so that's what we have as zone refining. Then comes the process which we call as vapor phase refining. Vapor phase refining. Vapor phase refining is based on the simple principle that we are able to convert the metal into a volatile compound which can be vaporized and then decomposed to give the pure metal back. Is it clear? Fine. So what we have is that we are able to, Prasad, you said that you are going to, Durga Prasad, you said that you are going to ask your friends to join the session. Where are your friends? Okay. We are teaching you in absolute English for the benefit of the students who are not able to understand Hindi, and it is also for the benefit of the students who want to improve their English, because MBBS will be taught in English. So you have to facilitate, you have to benefit the friends of yours who are not able to study, because most of the teachers are speaking in Hindi. Okay. So when we talk about the vapor phase refining, this method, the metal is converted into its volatile compound which is collected and decomposed to give pure metal. The two requirements, the two necessity, the metal should form a volatile compound with an available reagent. And this available reagent should not be that costly that we can't even use it. And that available reagent should be stable enough to be recycled. Okay. Then the volatile compound should be easily decomposable so that the recovery is easy. Easily formed, easily decomposed. That's what it should be. Now here we have the Mons process for refining of nickel. We are going to talk about two processes. One is called the Mons process, the other one is called Van Arkel de Boer's method. Normally it is termed as simply Van Arkel method. Is it clear? So here nickel is reactive with carbon monoxide at around 330 to 350 Kelvin. So 330 Kelvin would turn out to be how much? 27 plus 30, 57. Maybe 50 to 75 degrees Celsius, something around that, 50 to 75 degrees Celsius. Now at that time nickel forms a complex with carbon monoxide, tetracarbonyl nickel, and it's a covalent compound, it's a molecular compound. Being a molecular covalent compound, it is volatile. It gets converted into the gaseous form. And then this is decomposed at a temperature of something around, it would be what? 175, that is 175 to 200 degrees Celsius. So it is near about approximately, it is going to be 200, 175. Yeah, approximately 200 degrees Celsius. So it decomposes at 200 degrees Celsius. So it is something like, here we have nickel. Let's say we have a table here. Here we have the piece of nickel, Ni, and we heat it here to 50 degrees. And here we have the stream of carbon monoxide. Here this nickel piece is going to be consumed. Here we are going to have it heated to a temperature of 200 degrees Celsius. And here the nickel will keep on depositing and carbon monoxide will move further. Now this carbon monoxide is recycled and more of the nickel is pushed over. Now this is what we have as the Mons process. Okay. The next process that we use is called Van Arkel de Boer's method. This Van Arkel de Boer's method is used for zirconium, this is used for titanium, and here we are creating the iodide. Now what do? Zirconium or titanium, like this is the case, this is the container. Here we have the impure metal and we simply heat it. It is being heated at a lower temperature. Here we have a filament, a tungsten filament. This is a tungsten filament. This is the tungsten filament. So here it vaporizes, goes to this tungsten filament and deposits here. Iodine is released back. Here it is iodine. So this keeps on shifting from here to here to here to here, and this again keeps on depositing, and a layer of very pure titanium or zirconium is formed on the surface of the tungsten filament, which is drilled from the tungsten filament, from the zirconium or titanium, and is reused. So that is how we are able to create very pure zirconium or titanium. That is what we have as the vapor phase refining Van Arkel de Boer's method. It is zirconium or titanium which is being used. Yeah, Poonam Singh, anything you want to ask? Anybody has to ask anything? Like में बड़े आलसी हो गए. Now this is what we have as chromatography. Now chromatography is kind of a method wherever any kind of physical or chemical difference in the species, and we can use chromatography for it, physical or chemical. Nuclear difference won't work. Like we cannot separate ortho and para hydrogen using chromatography. Okay, we won't be able to separate out activated cobalt and non-activated cobalt having the same mass. But chromatography can even be used to separate on the basis of density. It can be used to separate on the basis of basic character or solubility or adsorption, anything, any physical or chemical difference in the property, and chromatography can be used for that. Because chromatography as such is not something in itself, it is this material which is being filled inside that chromatographic column which is responsible for the separation. Now this material, how it interacts with the substance we are pouring in it, that is dependent on the difference in the physical and the chemical properties. Is this clear? So this is what we have as the chromatographic column. Okay. Now this is what we have as the column chromatography. It can be used to differentiate, or it can be used to separate the lanthanoid elements. It can be used to separate the actinoid elements, because they have very similar chemical properties, but still they differ from each other in some quantities, some properties. Is it clear? So here we talk about something called chromatography. Now these metals, should I tell you what the use of the metals are? It's something like in the younger classes we used to tell, there was a question, what is the use of water? What is the use of water? Water is being used for everything. Water is responsible for our life. But we used to tell, water is used for washing, water is used for drinking, water is used for bathing. Tell 5 uses of water. Water is used for cooking, water is used to wash clothes. Similarly, when we talk about the uses of metals, metals are going to be used everywhere. Whatever you might do, some or the other metal is being used. Like metals, aluminum foils are used as wrappers for food material. The fine dust of the metal is used in paints and lacquers. Aluminum, being highly reactive, is used in the extraction of chromium and manganese from their oxides. It is used in thermite process. Wires or aluminum is used as electricity conductor. The overhead wires are not made up of copper, it is made up of aluminum, because aluminum has a lower density. हवाई जहाज भी aluminum के बनते हैं. Okay, aluminum के केन बनते हैं. Fine. So that is what we have as the use of aluminium. Copper. Copper हमें मग बनाने में काम आता है, कढ़ाई बनाने के काम आता है. Copper is used to make wires. Copper is a very important metals, and there was something called Bronze Age. Bronze is an alloy of copper, used in several alloys that are rather tougher than the metal itself. Brass, bronze, coinage alloy with nickel. So this is what we have as copper. Use of copper. Okay, fine. Zinc. Now zinc use might be there because many people don't know where the zinc is being used. Zinc is used for galvanizing iron. Maybe you have seen the galvanized pipe, GI pipes, what we call the water pipes which are used in housing. Those silvery white pipes, they are zinc coated iron pipes. Zinc is coated on the surface of the iron to prevent its rusting. So that is what we have as the GI pipes, the galvanized iron pipes. That is used in batteries. Your dry cell, they have container, zinc container in it. It consists of many alloys, brass, bronze, the German silver. Zinc dust is used as a reducing agent in the manufacture of dyestuffs, paints, etc. Zinc is also used in extraction of gold as a reducing agent. Common, easily available. And then we talk about iron. Do I need to tell you the use of iron? You don't know? चलो छोड़ो, अगर नहीं पता तो रहने दो. लोहा कहाँ इस्तेमाल होता है? So that's the end of the chapter for us. This offer is now no longer. 2 p.m. Swati Batra ma'am is going to take the class, and remember, tomorrow 10 a.m. you have the class with Anoop Vashishtha. And tomorrow we are going to start with the chapter, Khatarnak, Bhayankar chapter called Chemical Equilibrium. If anybody is there here who has not joined with the special classes, go ahead and join with the special classes using the code AVLIVE. Join with us. So tomorrow it is Chemical Equilibrium. Tell everybody, tell your friends that you have to join this particular batch called Chemical Equilibrium. It is going to be a long class. because somehow 1 hour class doesn't suit me. मेरे को पता ही नहीं चलता क्लास कब शुरू हुई कब खत्म हुई. And when we are talking about these chapters, भैया सुबह सुबह नाश्ता कर लेना 10 बजे से पहले, ठीक है, नाश्ता करके बैठना. Then 2 p.m. we have the class with Botany, Swati Batra ma'am. 3 p.m. Sachin sir is gonna have the class, and 4 p.m. again Chemical Equilibrium Part 2. ठीक है. So meet you tomorrow at 10 a.m. Join our Telegram channel, YouTube classes, PDFs, everything. t.me/NEET Elixir, a simple name. Join here. Download the Unacademy app. And this is my page on Unacademy. Unacademy.com/Anoop Vashishtha is my page. Follow me. And let's see. Special class plus classes. Subscribe on the NEET Elixir by Unacademy for the best live classes. Like, share and subscribe. And please share it with your friends. Don't go anywhere. We are just starting with the special combined session where we are going to talk about something, isn't it? So, meet you in a few minutes. How many minutes? 8 minutes. So, be there. In 8 minutes, we are going to start the class once again. Bye-bye. Take care. Good day and stay tight.